Right, in this video we're going to look at how to balance redox equations. So we've got a electrochemical and electrolytic cell here, so let's have a look at this electrochemical cell for a start. The first equation I want to write is the reduction equation, and here the reduction is, we've got copper on the right hand cell and zinc on the left hand cell, so these are the two redox potential, copper and zinc. So we want to use these two because copper redox couple is the most positive, it's going to be reduction, so let's put down copper. The copper sulfate is in an aqueous solution, so the copper ions are going to be aqueous. We're then going to it's going to change from copper 2 plus into copper. We notice here that this is an electrode, so it's going to be copper and it's going to be solid. So to balance this half equation, I'm going to make sure that there's the same amount of coppers on both sides. There is. So now we're going to add 2 electrons to balance the charge. The charge is 2 plus on the left and 0 on the right, so we're going to add 2 electrons to the most positive side, and that's on the left here. So this is our first half equation balanced. We're then going to do a second half equation. We've done a redox half equation, which is the redox couple goes forwards, and now we're going to do the oxidation one, so the redox couple will go backwards. We're going to start with the zinc. It is a solid because it's the electrode here, so let's put its phase in. We're going to turn it into, zinc nitrate of the ions here, and we can see the couple it turns into is a zinc 2 plus ions. It's in an aqueous solution, so it's going to be aqueous. To balance the charge, left hand side is negative, the right hand side is plus 2, so let's add 2 electrons. Now notice how these electrons are, there are 2 electrons gained by the copper ion and 2 electrons lost by the zinc metal atom. So there is an equal exchange of electrons. So we're just going to cancel those and then write the full equation, which is, we're going to write copper 2 plus aqueous plus the zinc solid goes to the copper solid plus the zinc aqueous. And this is our fully balanced equation. So this is a straightforward one where the number of electrons gained and the number of electrons lost are equal. Let's have a look at the next one. Here we have an electrolytic cell. There's power supplied to this cell, and we've got this reaction happening. On the right hand electrode here at the cathode, we can see copper being produced, and on the left hand electrode we can see this gas being produced, this pale green gas, which is most likely chlorine from the chloride ions. Anyway, if we look here, the 2 actual redox couples are going to be involved here is the copper 2 plus the copper couple and the chlorine to chloride ion couple. Now, because this is an electrolytic cell, actually the most negative one is going to go forwards. The other way we can look at this, or as a reduction, is that if there are copper ions and there's chloride ions present originally, we have to start our reaction with the copper and chloride ions. So the first half equation is this copper again. It is aqueous because it's dissolved in an aqueous solution. We're going to add 2 electrons. I know this because I just did it above. I kind of did this in the wrong order. Let's add the chloride ions now. So we have a chloride ion, okay, and it's going to go to chlorine. So this is oxidation. It's going to go backwards. It's aqueous. It's going to go to chlorine, the gas. Okay, so now we need to balance this. This is a bit harder to balance because it's not just balancing the electrons. We have to balance the atoms first. And the ion electron method, we haven't got oxygens or hydrogens. We don't have to worry about balancing those. But the first step anyway is to balance those atoms that aren't oxygen or hydrogen. That's the chlorines. Because this is a diatomic molecule on the right, there are 2 chlorines. We need to make sure there's 2 chloride atoms on the left-hand side. We are going to add electrons to the right-hand side to balance out the negative charge. There is a 2 minus charge because of the 2 chloride ions on the left-hand side, so we need 2 electrons. Again, notice that these 2 half equations both have 2 electrons gained and 2 electrons lost. So we're going to cancel those electrons and just add and take the terms straight down into our final equation. First term, copper 2 plus aqueous, plus the second term, coefficient, keep the coefficient in front of it, so 2 chlorides, aqueous, they're going to go to this copper solid, and the last term is this chlorine gas. And these are 2 balanced full equations from the half equations. So we're adding a reduction and an oxidation half equation to make our full equation. Okay, let's look at one that's slightly more complicated. So in this case here, we've got an electrochemical cell set up. The right hand cell has copper solid and chromium ions, and the left hand side has magnesium solid and magnesium ions. So these ions are in an aqueous solution here. I haven't stated that, but let's assume that they are. We can, if we look at the two redox couples, we can see we have for the chromium ion to chromium, it's a negative 0.74 volts, and the magnesium 2 plus to magnesium, it's negative 2.37 volts. The most positive reduction couple here is the chromium one, so that's going to be the one that's reduced and goes forwards. So the first term I'm going to write is the chromium ion. It's aqueous. It's going to turn to the chromium metal. Look at the redox couple. Obviously it's an electrode here, so it's solid. And now, so we've got the atoms are balanced here. There's one chromium on each side, so let's balance the charge. We're going to need electrons, but because the charge was 3 plus here, we're going to need 3 electrons. So that's our chromium or reduction half equation here balanced. Let's do the oxidation one. If the reduction half equation went forwards, obviously the reduction one goes backwards. We're going to start with the first term as magnesium. Notice that the magnesium here is in the solid form in the electrode. We're going to turn it into magnesium ions. We're going from magnesium to magnesium 2 plus ions. Notice how we now have a 0 charge on the left hand side and a 2 plus on the right hand side. So we're going to add some electrons. We need to add 2 electrons to balance it. Now, how this is more complicated than the one beforehand is if these two half equations, the first equation which is the reduction and the second one which is the oxidation, are going to exchange electrons evenly, we need to change the number of times each reaction happens so they have an equal exchange of electrons. So what we do is we look at the two numbers, the coefficients in front of the electrons of the two different equations, 3 and 2, and we just work out what is the lowest common denominator, number that they both go into, and that is 6. So we're going to have an exchange of 6 electrons. So we're going to multiply our first equation by 2, so that we will get 6 electrons, and multiply the second equation by 3, so we will get 6 electrons. We're going to rewrite these equations out in full here. So let's go 2 chromium 2, because we've multiplied this by 2, it's 2 chromium aqueous ions. We now have 6 electrons because we multiplied by 3, and they will form 2 chromium solid atoms. Okay, that's fine. Let's do the magnesium one. We're going to multiply it by 3. So we're going to go 3 magnesium solid goes to 3 magnesium ions plus 3 times 2 is 6 electrons. Notice now we've done that multiplication. If we chose the correct numbers, we have the equal amount of electrons both on the top and the bottom. We're going to cross those out because we're not going to bring them down to our final equation. Let's put the terms down into our final equation. We're going to start with the chromium at the top. There it goes. And then we're going to add the magnesium on the second equation on the left-hand side. There we go. And then we're going to go towards 2 chromium solids plus 2 magnesium 2 plus. And that's our balanced equation. So it's as simple as choosing the right number to multiply your equation by so that the number of electrons is equal and we can cancel them. We can get a fully balanced equation done. Okay, let's have a look at another example. So here is an electrolytic cell. We have these 2 redox couples that go with the cell. We have chromium and iodide ions. Okay, chromium iodide here. It's in the liquid form because it's molten. So let's write the reduction equation. Because this is an electrolytic cell and electrical energy is provided to make the reaction happen, actually in this case the most negative is going to be reduction. Or if we think about it, the chromium 3 plus ions are in the solution here and iodide ions, so we must start with chromium 3 plus. So chromium 3 plus, now in this case it's not aqueous because it's not dissolved in water. It's an ionic solid that has been heated up until it's liquid. So these ions are in the liquid phase. We're going to turn into chromium, but in this case we've got a pool of chromium here, and that's because it's so hot the chromium's gone to a liquid. Okay, sometimes it might be a solid. In this case I've called it a liquid. So we need to balance this equation. We're going to add electrons, but we need 3 of them to balance out the 3 plus charge, and that is our reduction equation balanced. So oxidation equation, if the reduction one is going forwards, oxidation one is going backwards, we're going to start with I minus. It's in a liquid form. We're going to turn it into I2, the gas, and we need 2 I minuses to balance the 2 iodine atoms that are in the iodine molecule here. So now we have a charge of -2 on the left hand side, so we need to add 2 electrons to the right hand side. So this is similar to the last equation in that we need to multiply the first equation here by 2 and the second one by 3 so that we get the number 6, which is the lowest common denominator that 3 and 2 go into. So let's rewrite these out again. We've got 2 chromium 3 pluses because we multiplied it by 2, 6 electrons go to 2 chromium liquids. We have 6 I minuses, they turn into 3 I2s, and 3 times 2 gives us 6 electrons. Cancel out those 6 electrons, and we can now put these down into our final fully balanced equation. Take the first term down, which is chromium 3 plus, then let's take the second one, which is plus 6 I minuses. Third term, well, let's put an arrow first, 2 chromium liquids here, and then the fourth term here is a 3 I2 gas, and this is our fully balanced equation. Okay, let's have a look at the last equation I have for you today. So the last equation here, we have a mixture of aluminium oxide. It's molten again, it's as a liquid. This is also an electrolysis or electrolytic cell electrolysis reaction. So power is being supplied and it's making the reactions happen in the reverse direction they normally would. So the most negative one is going to go forwards. That's going to be our aluminium 3 plus turning to aluminium. So let's put that down. Aluminium, because it is molten here, it's in the liquid phase. We're going to turn it into aluminium, and when the aluminium metal is made, it's going to melt, so it's going to be liquid. Let's add the electrons to balance this. We need to add 3 electrons to balance the 3 plus charge. This is our redox equation, all balance. Let's do the oxidation one. This is going to go backwards, opposite direction to the reduction one. So we're going to start with O2 minus. It's going to be in the liquid phase as well because it's a molten solution of ions. We're going to turn it into O2 gas. Now remember here that we look carefully when we have A2 down the bottom. This is a diatomic molecule here. We need to make sure that we have 2 atoms on the other side. Now if we're using the ion electron method, usually we'd say, well, if we've got an imbalance of oxygens, we need to add water. That is not true if you already have oxygens on both sides. So in this case, we're just going to add another O2, or we're going to put a 2 in front of it. So now we have a charge of 4 minus on the left and 0 on the right, so we're going to add 4 electrons to the right. Okay, so this 3 and 4 do not cancel out. They don't cancel each other out equally, so we need to find the lowest common number they both go into, which is 3 times 4 is 12. So we're going to have to multiply the top one by 4 to make 12 electrons and the bottom one by 3 to make 12 electrons. Let's rewrite out these 2 equations again. We're going to have 4 aluminium 3 pluses, and we're going to have 12 E minuses. It's quite a lot, but that's how we do it. We're going all the way to make 4 aluminium liquids here, and then we're going down to make 6 O2 minuses, going to 3 O2s, plus 12 electrons again. Now, because we have the correct number of electrons on both being gained by the reduction half equation and lost by the oxidation half equation, we are going to cancel those out. Then we're going to write the terms. We're going to bring them down to our final balanced equation. So we've got aluminium 3 plus liquid plus 6 O2 minus liquid goes to 4 aluminium liquid and 3 oxygen gas. Now, if you're worried, is this final equation balanced? How can I check it? Well, what we do is we count the charge on either side. So here we have 4 and aluminium ions, and each aluminium ion is 3 plus, so we have a charge of plus 12, 4 times 3. Here we have 6 oxide ions, that have a charge of 2 minus. So the overall charge is minus 12. So we have plus 12, minus 12. Overall charge on the left-hand side is 0. Look on the right-hand side, we have a neutral atom here and a neutral molecule. So we have no charge on the right-hand side. The charges are balanced. Finally, let's check that the right number of atoms are on both sides. 4 aluminium atoms on the left, 4 on the right. 6 O's on the left, and 3 times 2, 6 O's on the right. This is correctly balanced. Hopefully this video helps. Hey, if I've gone too fast, go back, watch the video again if you need help with balances. Good luck balancing these redox equation. Good luck.